Let's explore balanced binary search trees. These are specialized binary search trees that maintain a certain balance in their structure. This balancing act guarantees that most operations can be performed in O log n time, where n is the number of nodes. We'll focus on two main types of balanced binary search trees, AVL trees and Red-Black trees, which are popular for their efficiency and widespread use in computer science. Why do we need balanced trees? To understand this, let's compare a balanced binary search tree with an unbalanced one. In a balanced tree, the operations take O log n time because the height of the tree is logarithmic with respect to the number of nodes. However, in an unbalanced tree, in the worst case, these operations can degrade to O n time because in the worst case the height can become linear. Therefore, balanced trees are essential for maintaining efficiency, especially when dealing with large amounts of data. An example is a balanced binary search tree on the left and an unbalanced binary search tree on the right. Let's begin by understanding AVL trees. AVL trees are self-balancing binary search trees where the height difference between the left and right subtrees cannot exceed 1 for any node. They were named after their inventors, Adelson-Velsky and Landis, who introduced them in 1962. They are considered the first dynamically balanced trees to be invented. AVL trees maintain a strict balance to ensure optimal performance. Thus, the operations such as insertion, deletion, and search can be performed in O log n time in the worst case. AVL trees use rotations to maintain balance after insertion or deletion operations. Two fundamental rotations are left rotation and right rotation. A left rotation involves rearranging nodes such that a right child becomes the new parent. Conversely, a right rotation involves rearranging nodes so that a left child becomes the new parent. These rotations help to rebalance the tree, ensuring that the height difference between the subtrees remains within the allowed limit. The diagram shows how the tree rebalances from before to after rotation. The balance factor of a node in an AVL tree is the height difference between its right subtree and its left subtree. It's calculated as the height of the right subtree minus the height of the left subtree. In an AVL tree, the balance factor must be -1, 0, or 1 to maintain balance. Here's a simple code snippet to get the balance of a node. The AVL property states that the absolute value of the balance factor must be less than or equal to 1. Now let's dive into Red-Black trees. Red-Black trees are self-balancing binary search trees where each node has an extra bit that denotes the color, either red or black. Rudolf Bayer invented them in 1972. Red-Black trees have less strict balancing compared to AVL trees, making them excellent for situations with frequent insertions and deletions. They're used in many language standard libraries. Similar to AVL trees, Red-Black trees also ensure that operations take O log n time in the worst case. In the diagram, black nodes are in solid black color and red nodes are in solid red color. Red-Black trees adhere to 5 key properties. Firstly, every node is either red or black. Secondly, the root node is always black. Thirdly, all leaves, which are typically represented as null or nil nodes, are black. Fourthly, if a node is red, then both its children must be black. Finally, all paths from any given node to its descendant leaves contain the same number of black nodes. This property ensures a balanced structure. In the diagram, nil nodes are shown as black rectangles. The insertion process in Red-Black trees involves several steps. First, we insert the node using the standard binary search tree insertion method. Next, we color the new node red. Then we fix any violations of the Red-Black tree properties that may have occurred due to the insertion. This fixing process involves recoloring nodes and performing rotations as needed. Finally, we ensure that the root node remains black. A simplified insertion algorithm is presented, including the essential fix insertion function. Let's compare AVL trees and Red-Black trees. AVL trees have a strict balance condition, where the absolute value of the balance factor is less than or equal to 1, while Red-Black trees have a relaxed balance condition. The height of AVL trees is approximately 1.44 times log base 2 of n, while the height of red-black trees is approximately 2 times log base 2 of n. AVL trees offer faster search performance, but red-black trees have fewer rotations during insertion and deletion. In terms of memory, AVL trees require storage for a balance factor, which is 1 to 2 bits, while red-black trees only need 1 bit to store the color. AVL trees are best suited for applications with frequent lookups and infrequent updates, whereas red-black trees are ideal for scenarios with frequent insertions and deletions. Therefore, choose AVL trees for search-intensive applications and red-black trees for write-intensive applications. Balanced search trees have various applications in real-world implementations. They are commonly used for database indexing to enable efficient data retrieval, file systems for organizing directories and files, computational geometry for spatial data structures, network routing for IP address lookups, and symbol tables in compilers and interpreters. You can find them in languages like Java in the 3map and 3set classes, C++ in the standard map and standard set classes, and even in the Linux kernel's completely fair scheduler. Additionally, they're used in PostgreSQL for gist indexes and in the Python sorted containers library. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.